In this video, we're going to go over the concept of spectrophotometry, and that is a totally weird word the first time you hear it, but it's something that we'll use a lot in chemistry and in AP chemistry and even organic chemistry. So spectrophotometry is how we can use the amount of light absorbed by a chemical, specifically a colored solution, to determine the concentration of that solution. Okay, so the darker the solution is, the more light that it's going to absorb, and thus the greater concentration that's going to be present. Now, when we perform an experiment with spectrophotometry, which this will be hard to understand through this video, but hopefully you'll get when you do your labs, is that we want to use the wavelength that is absorbed by the solution. The color that you see, so for example, if I have blue here, this is blue, just because we see blue, that actually is not the color that's being absorbed. If we want to think about that, and I'm going to skip ahead just a second, we'll get there. The color that we see is, so this is what we see. Its complementary color, so the one directly across from it, is what is absorbed. Okay, so if you see violet, that's what you see, but the color being absorbed would be yellow, and yellow light has a range of wavelengths between 560 and 600 nanometers. Okay, so what we're going to do is we're going to show you how to create a spectrophotometry experiment. So let's say you come to class one day and you have a beaker and it's just some unknown blue solution. And all you know is that it's copper sulfate. Okay, that's its identity. But its concentration or its molarity is unknown. So what we would do is we'd say, okay, let's make a whole lot of copper sulfate solutions. I'm just making a lot of them here. And let's know their molarities. So let's say their molarities, let's make a 1 molar, a 2 molar, a 3 molar, a 4 molar, and a 5 molar. And what we see by chance is that this blue solution falls somewhere between 2 and 3. Okay, but we don't, so it must be 2 point something or less than 3 molar. Okay, but we don't know exactly the exact concentration, and that's something that we'd like to find out. So what we're going to do is we're going to take our molarities, our 1 molar, our 2 molar, our 3 molar, our 4 molar, and our 5 molar, and we're going to plug them into a machine called the spectrophotometer. The first thing we would do is say, okay, copper sulfate's blue, so we would set it to an orange wavelength. And I've worked with copper sulfate a whole bunch. We'll talk about how you know the exact wavelength, but it would be about 630 nanometers. Okay, and you just turn the machine to that. That will not be hard. And you then zero the machine. And this is going to be weird to understand over video, and I'm not going to test you on that. But you need to do this when you perform this experiment, is just like you zero a scale, you zero a spectrophotometer. And the way you do that is you zero it by adding distilled water, and you tell the machine that this should read 0 absorbance. Okay, absorbance is how we're going to measure this. And absorbance is just a fraction. What percent, as a decimal, what percent of the light actually passed or got absorbed by your sample? Okay, so if I have a laser of orange light, it should just pierce right through there, okay, because water is not going to absorb that. Now, if I go to this 5 molar, okay, we have a orange light that's passing through there. Maybe only a little bit of the orange is going to actually exit our beaker because it's being absorbed by the solution. And then what I'm going to do, and this won't take long when you do it, is I'm going to put in each sample my 1 molar, read its absorbance. I'm going to put in my 2 molar, read its absorbance. I'm going to put in my 3 molar, read its absorbance. 4 molar, read its absorbance. 5 molar, read its absorbance. And then I can make what's called a calibration curve. And what I'll do is I'll use Excel. We're not going to do that here, but I'll get a y equals mx plus b equation. And then what I'll do is I'll plug in this to my machine, and I'll say, oh, it gave me my unknown, and I'm going to do that in pink, my unknown. It gave me an absorbance of 0.45. So using y equals mx plus b, although I'm not doing that here, I'm just doing it graphically, I can see, oh, this concentration's, and maybe that's not perfect, this concentration is about 2.3 molar. And so now that concentration is no longer unknown, it's 2.3 molar. Okay, so let's see exactly how this will work with some practice problems. Beer's law is what this law is actually called, where capital A is the absorbance, lowercase a is something called the extinction coefficient, or the molar absorptivity, and this is unique to each chemical. B is the length of your cuvette. That's the length of the piece of glass that you're actually putting into your machine. It'll look like a test tube, but it'll actually be a cuvette. And they're almost, I've actually never seen a case in terms of actually being in lab where they're not 1 centimeter. So mathematically, this will just be 1 centimeter and not influence your answer one way or the other. And then C is your concentration and molarity. And so what we get is y equals m. This makes sense. Y is this y absorbance. If we look, there we go. M is our slope, and then C is concentration. That should be x. So this equals y equals mx, and then chances are when you do this in real life, you will get a y-intercept. But in a perfect world, you should not get a y-intercept because 0, when x is 0, when our concentration is 0, it shouldn't be absorbing anything. Okay, so this says consider a 0.2 molar solution of cobalt chloride. I'll tell you that cobalt chloride is going to be red. And it has an absorbance of 0.27. Okay, so this is what we've graphed. Molarity of 0.2, absorbance of about 0.27. And then we have a 0.5 molar solution, and its absorbance is 0.69. Again, that's graphed. And we've plugged this into Excel, and they give us a graph. So we want to know the molar absorptivity constant of cobalt chloride. That is just our slope. So what we're going to do is we're just going to calculate slope. If you remember from math class, slope is, one of the equations for slope anyway, is y2 minus y1 over x2 minus x1. One of my y values is 0.69. The other one is 0.27. The x value that aligns with 0.69 is 0.5. And the x value that aligns with 0.27 is 0.2. And I will plug that into my calculator. And I'm going to get 1.4. And here's what's really weird, and I'm not super worried about the units here. The units for y is absorbance, ABS. And the units for x is concentration, which is molarity. So this technically is ABS over molarity. So now they say we have an unknown cobalt 2 chloride solution, and it's got an absorbance of 0.38. So watch what we can do. We could say, oh, here's about 0.38. And when I plug this in, just eyeballing it, we should get about 0.272826, something about that for the concentration. But watch what we can do that's even better. We can say y equals mx plus b. We will assume that we don't have a y-intercept here because we don't have any information on that. But y equals m. We know that the extinction coefficient is our slope, 1.4x. And so now we can just plug in the 0.38. Now, is that going to be plugged in for X or for Y? Well, it's an absorbance, so if we look at our graph, absorbance is Y, so this should be 0.38 equals 1.4x. We divide each side by 1.4, and our x actually gives us what we kind of estimated, 0.27 molar. Okay, so how do you know which wavelength to set your spectrophotometer to? You want to find the maximum absorbance of whatever your compound is. This will be in the range of your complementary color. Okay, so we've already talked about complementary colors in the color wheel, so I'm going to erase these. Now, we have crystal violet, and if you had to take a guess, that would be violet in color, and it is. Now, crystal violet absorbs, or excuse me, is violet. So that's what we see. It absorbs in the yellow range. And that range is 560 to 600. So how do you know exactly what number to set your spectrophotometer to? Because if I wanted to do 567, my spectrophotometer will allow me to. So what I need to do is I look at the absorption spectrum, where we look at different wavelengths, just a whole bunch here, and we see where crystal violet absorbs the best. And we see this peak is going to be, what is that, about 590. 590 nanometers is the maximum absorbance for crystal violet. Okay, chances are if you set the machine to 550, it would do okay, but it's going to have its best results when you're at its highest or its maximum absorbance. Okay, so let's do some practice questions and we'll call it quits with this video. A lab technician is given the task of determining the concentration of nickel sulfate, which would be green. The technician measures the absorption spectrum of the unknown concentration nickel sulfate solution over a range of wavelengths. And in A, it says identify the optimum wavelength for this analysis. So go ahead, pause the video, try to figure out the best wavelength to set the machine to. I'm going to say about 715 nanometers. This is the maximum absorbance, or this is, excuse me, the wavelength where the maximum absorbance occurs. Okay. The technician has a stock solution of 1 molar nickel sulfate. The technician dilutes the stock solution, and so we get 0.4 molar, we get 0.32 molar, we get 0.24 molar, we get 0.16, and we get 0.08. And we want to know explain the procedure that was used to get this graph. So the first thing we would do is we would zero the machine with a cuvette filled with distilled water. We would find the wavelength where the maximum absorbance occurs. Remember, that's lambda, which is a wavelength sign. Find wavelength where maximum absorbance occurs and set machine to this wavelength. Measure the absorbance of your known samples. That's what we've done here, where we've measured the absorbance. Oops, and I need to get a little bit better with my lines here. Okay. Measure the absorbance of your known sample. We were going to graph absorbance versus concentration. We're going to generate a line best fit. And now we have this graph. So in C it says the unknown solution is measured to have an absorbance of 0.75. Determine the concentration and justify your answer. So we don't have any numbers here as far as the absorbances, so I don't know that I have a y equals mx plus b, because that's what I would normally do where we're given an absorbance. We can plug it in for y and solve for x. Here's what I would do. I'm going to do this in pink again. Here's where 0.75 absorbance is, so let's line that up. It intersects right about there. And so I'm just going to estimate this. The unknown solution has a concentration of about, and I don't know, 0.31 molar. So we plugged in 0.75 to the y-axis, and we saw the x-coordinate. Okay, last question here. So, in D it says, the lab technician submits the results of their work to their supervisor. The lab technician is terminated for 2 reasons. Fingerprints were left on the cuvette, we'll talk about that, and the same procedure that we've been talking about was followed to determine, which I spelled wrong, the concentration of a sample of NaCl. Explain why the termination was justified. So I'm just going to talk through here, and you can write down your answers here. Sodium chloride cannot be used for spectrophotometry. Think about what color salt water is. If I was on a boat in the ocean and I took a glass and I got a glass filled with salt water, it would be clear. So we need colored solutions for spectrophotometry. So that's one reason. And then a second reason is that if I have fingerprints, and that's my way of drawing fingerprints here, on my glass versus no fingerprints, if I have orange light coming through, some of it's going to get absorbed and we're going to have less come out at the end. But if I do the same thing and I have this, some of it gets absorbed, the fingerprint will absorb some and will have even less. So it'll make it seem like the absorbance is way too high.